Good afternoon, everyone, and welcome back to the afternoon session. In the first half of this session, the afternoon session, we have three talks. And the first speaker is Hami Mehrabi. He's going to tell us about the optimal convergence rate in trace distance and relative entropy for the quantum central limit theorem. Please start.
Good afternoon. Hi. First, I want to thank the organizers for preparing us this stage. Today, I'm going to talk about our recent finding regarding optimal convergence rates in trace distance and relative entropy for the quantum central limit theorem. This is a joint work with Salman, Beigi, and Milad, Goodarzi. I want to start from classical setting, central limit theorem in the classical setting, to convince you that this is a fundamental result in our modern mathematics, and to show you some counterparts of our results in the classical setting. I can say that the literature of central limit theorem goes back to the work by great mathematicians in 18th and 19th century, but the version of central limit theorem we know these days and we use these days was developed in 20th century. To talk about those results, let x1, x2 to xn be IID random variables with mean mu and variance sigma 2. Set Sn to be the normalized summation of n versions of IID random variables, and Z sigma to be the normal random variable with mean 0 and variance sigma 2. In 1921, for the first formal version of central limit theorem, Lindbergh and Levy showed that as n goes to the infinity, the CDF of Sn converges to the CDF of Z sigma in a pointwise sense. And regarding the convergence rate, Berry and Essin in 1941 showed that assuming the finiteness of third order moment, we can say that this convergence happens at the rate of 1 over square root of n. After these two results, mathematicians ask themselves, okay, now we have two nice results. What about central limit theorem in other metrics? A stronger metrics like total variation distance or an entropic version of central limit theorem. For the first one, central limit theorem in total variation distance, I can point to the work by Sirajinov and Mamadov in 1962. They showed that assuming under the same assumption as Berry-Essin theorem, and the additional assumption that the density of x1 has an absolutely continuous part, then we can say that Pn converges to phi sigma in the total variation distance at the rate of 1 over square root of n. Here, Pn and phi sigma are the density functions of Sn and Z sigma. And regarding the entropic version of central limit theorem, I can point to a kind of recent result by Babkov, Kisakov, and Gotze in 2013. They showed that assuming the finiteness of fourth order moment and the additional assumption that x1 has finite differential entropy, then we can say that Pn converges to phi sigma in the sense of relative entropy at the rate of 1 over n. I should mention that here these two convergence rates are optimal. These assumptions are essentially minimal. So to the best of our knowledge, these two results in the classical setting are the best known results for the central limit theorem in the sense of total variation distance or entropic version of central limit. Okay, I think I might lose the audience if I keep talking in the classical setting, so let's move on to the quantum setting, and let's start with our main results. In this work, we just translate these two results to the quantum setting. For the first result, we showed that for ρ, a centered M-mode bosonic quantum state with a finite third order moment, we can say that the n-fold convolution of ρ converges to a Gaussian quantum state with the same first and second order moments as ρ in the sense of trace distance at the rate of 1 over the square root of n. And for our second result, we showed that for ρ, assuming the finiteness of 4 plus delta order moment, where here delta could be any arbitrary positive, a strictly positive number, we can say that ρn converges to ρg in the sense of relative entropy at the rate of 1 over n. I should emphasize that here, these two convergence rates are optimal. We have an example for that. These assumptions are essentially minimal. We can build a bunch of examples to show that. So from our perspective, we just found the optimal convergence rates for quantum central limit theorem in the sense of trace distance and relative entropy, assuming essentially minimal assumptions. I'm sorry if you find it difficult to understand some concepts in these theorems. I will explain them later. Okay. I will dedicate the rest of this presentation to the proof ideas and methods we developed in this work. But before that, let me do a quick review on bosonic quantum systems, because I guess some people in this room might not be very familiar with those systems. Actually, I want to compare those systems with classical setting. In the classical setting, we work with random variables, which are usually real valued or d-dimensional real valued. In the quantum setting, all the magic happens in Hilbert spaces, and the Hilbert space of M-mode bosonic quantum system is isomorphic to the space of all square integrable functions over Rm. In the classical setting, we can define coordinates for a d-dimensional random vector. In the quantum setting, we have fundamental operators called annihilation and creation operators on each mode, where here Aj is the annihilation operator on the jth mode, writing using quadrature operators. In the classical setting, we can define mean vector and covariance matrix for a random vector. In the quantum setting, we can use the vector of all quadratures and define the vector of first order moments for a quantum state and covariance matrix. In the classical setting, we have a concept called a characteristic function. In the bosonic quantum systems, we can define a concept called quantum characteristic function for any trace class operator T using displacement operators. One thing you should remember here is that similarly to the classical setting, we have a nice identity called quantum natural identity, enabling us to relate the Hilbert norm of a trace class operator to the second norm of its characteristic function. In the classical setting, we have some nice distributions called normal distributions. In the quantum setting, we have a family of quantum states called Gaussian quantum states, which you can find one more thermal state here. Again, one thing you should remember here is that similar to the classical setting, we can fully determine a Gaussian quantum state using its first order moments and second order moments. That's why when I was talking about our main results, I defined rho g to be a Gaussian quantum state with the same first and second order moments, which is enough. In the classical setting, we can add different random variables, and in case they are independent, the resulting distribution will be the convolution of their individual density functions. In the bosonic quantum systems, we have a counterpart for this action called quantum convolution. For two quantum states, rho and sigma, we define the convolution of rho and sigma with parameter eta as this form, where here u eta is the beam splitter unitary with transmissivity parameter eta. Using this formula, we define the n-fold symmetric convolution inductively. For two quantum states, we set eta to be half, and for our induction step, we use this formula. If we are convolving n IR divergence of a quantum state, we use this notation rho n. A nice thing about quantum convolution is that it acts similarly to the classical setting in the level of characteristic function and covariance matrix, as we have these nice identities. Using these nice identities, we can write the characteristic function of rho n as this form and the covariance matrix of rho n as this form, which is exactly the way how the normalized summation of n IOD random variables in the classical setting behaves. Okay, before talking about our methods and ideas, let me do a quick literature review on quantum central limit theorem to compare our results with previous results. I can say the quantum central limit theorem has been started by the work by Cochin and Hudson in 1971. They showed that for rho, a centered M-mode bosonic quantum state with finite second order moment, rho n converges weakly to rho g, meaning that this convergence happens for any bounded operator x. And as we know, this is the same topology induced by the trace norm on the set of all quantum states. So actually, they showed that rho n converges to rho g in the sense of trace distance. But they didn't say anything about the convergence rate. For the convergence rate, I can point to a kind of recent result by Becker, Data, Lamy, Rose in 2021. They showed that assuming the finiteness of third order moment, we have rho n converge to rho g in the sense of Hilbert-Schmidt norm at the rate of 1 over square root of n. And using this convergence rate, they derived two other convergence rates for trace distance and relative entropy, which you can see here. Their proposed convergence rate for Hilbert-Schmidt norm was optimal, but these two convergence rates wasn't optimal, so the legitimate question to be asked, okay, can't we find the optimal convergence rates for quantum central limit theorem in the sense of trace distance and relative entropy? In our first work with Salman in 2023, we proved optimal convergence rates assuming stronger assumptions. For trace distance, we showed optimal convergence rates assuming the finiteness of maximum of 2m and 3 order moment. For relative entropy, we showed the optimal convergence rate assuming that rho satisfies an inequality called quantum Poincare inequality. But those assumptions were far from being optimal. Here is the example I promised you. These convergence rates are optimal, but the assumptions in that work were far from being optimal. Just a reminder, in our current work, we proved these two convergence rates, these two optimal convergence rates, assuming the third order moment for trace distance and 4 plus delta order moment for relative entropy. Okay, great. Let's move on to our proof ideas and methods. But again, before our proof ideas and methods, I want to tell you a story about the reason we see central limit theorem in the quantum setting or even in the classical setting. I will try to say that a story in the quantum setting, but the same story happens in the classical setting. Just a remark here is the forms of character function of rho n. Just as a first observation, we see that as n goes to the infinity, z over square root of n converges to the origin. So if you want to talk about the characteristic function of rho n, we should see how characteristic function of rho behave near origin. With that intuition in mind, let rho be a centered M-mode bosonic quantum state with finite moment of order 3. This statement, rho has finite moment of order 3, is roughly equivalent to the statement that the characteristic function of rho is 3 times derivative in the origin. So using that statement and the above intuition, let's write the Taylor expansion of log of characteristic function of rho near origin up to order 3, which we can see in this expansion. Just a quick comment, these coefficients in the classical setting are called the cumulants. So here we can call them the quantum cumulants. Let's compute some of those coefficients. You should believe me that as rho is a centered quantum state, we can simply derive that Q0 is 0, and all other coefficients that are related to the first order derivatives are 0 too. And if we look at the terms that are related to the second order derivatives and some of those terms, we end up having the function log of characteristic function of rho g. Why is that? It's because rho g has the same first and second order moments as rho. Putting all this together, we have this expansion for log of characteristic function of rho, which is the log of characteristic function of rho g, plus some other terms with degree greater than 3. Again, just a quick reminder, we had this form for the characteristic function of rho n, and we end up having this expansion for the characteristic function of rho n. And as you can see, just as a consequence of second order Taylor expansion, we derived having that the characteristic function of rho n converges pointwise to the characteristic function of rho g as n goes to the infinity. So there is nothing fancy behind having central limit theorem in the quantum setting or in the classical setting. Okay, let's use the next few minutes and talk about our proof ideas. Here is the story. We are interested in the distance between rho n and rho g. If you look at this distance in the level of characteristic function, we should be happy because we have some nice Taylor expansions called Edgeworth type expansions. If you look at this distance in the level of Hilbert-Schmidt norm, again, we should be happy because there exists a nice identity called quantum potential identity. But we were suffering when we looked at this distance in the level of trace distance and relative entropy. To overcome this difficulty, we developed two interesting lemmas which enable us to relate trace distance to the Hilbert-Schmidt norm and relative entropy to the Hilbert-Schmidt norm. And using quantum potential identity, we can relate those to the level of characteristic function. For the first lemma, we showed that for many arbitrary operator T, such that A dagger TA is a trace class operator, where here A is the multiplication of all annihilation operators, we can bond the trace norm of T using the Hilbert-Schmidt norm of A dagger TA. And for the second lemma, we showed that for rho, an M-mode bosonic quantum state and with finite n+3 order moment, for any generic thermal state tau, we can bond the relative entropy between rho and tau using the Hilbert-Schmidt norm of rho minus tau times a power of number operator. Just a quick comment, we strongly believe that these two lemmas could be helpful in some other concepts like quantum tomography or quantum learning. So that's my comment. But in our work, these two lemmas were not very useful on their own. Why is that? Because just look at the conditions on moments. For example, suppose we want to use the first lemma and handle the trace norm of rho n minus rho g. As we want to A dagger TA be a trace class operator, rho should have a finite 2m order moment, which we don't have that assumption. We just wanted to handle that trace norm, assuming the finiteness of third order moment. So we should develop another method which is called the truncation on the focus states. Let pi n be the projector operator onto the subspace of all quantum states with at most n particles. Let rho n be the projection of rho onto that subspace, and let sigma n be the normalization of rho n. Here, sigma n is a legitimate quantum state, but it is not centered. Let's make use of a displacement operator and make it centered, called it sigma tilde n. We showed that we can handle the trace norm of rho n minus rho g with the trace distance between n-fold convolution of sigma tilde n and its classification version. And we can again handle the relative entropy between rho n and rho g using the relative entropy between n-fold convolution of sigma tilde n and its classification version. The point here is that now sigma tilde n has finite rank. Its moments are finite up to any order, so we can use previous lemmas to handle the distance between n-fold convolution of sigma tilde n and its classification in the sense of trace distance and relative entropy. To conclude this presentation, we proved optimal convergence rates in trace distance and relative entropy for quantum central limit theorem. Assumptions are essentially minimal and cannot be weakened. We developed two interesting lemmas. We strongly believe that those two lemmas can be very helpful for the community relating the trace norm and relative entropy to the Hilbert-Schmidt norm. And we suspect that these assumptions are necessary too. That was my talk. Thank you for your attention. And if you have any question, I would be happy to answer. Thank you.
Thank you for the great presentation. Any questions?
What is the physical motivation for considering states that have unbounded higher moments?
Physical motivation, I guess that was just mathematical motivation.
Okay.
Hello. So I wanted to ask, what are some potential applications of your results to, say, something like ergodic theory equivalent in that space, or I don't know, some other ideas?
Oh, that's a great question. We don't have any good application of these convergence rates yet, but I heard from some great researchers that they might be useful in some algorithms in quantum key distribution or something like that. But I'm not very familiar with that algorithm.
Yeah, because it sounded like, for instance, like in MC methods, we rely upon the ergodicity of, like, for example, our Markov chains. So maybe we could define some, I don't know, say stochastic process using like this operations in your space, which maybe could be useful in some context.
Oh, that's nice.
Hey, thanks for the nice talk. So I've seen this applied this Cauchy-Hudson theorem, right? And this extremality of Gaussian states paper of Michael Wolf and other people, I don't remember. So to show that, like, essentially certain measures are extremal on Gaussian states. So they among all states with fixed moments. So I don't know, with your central limit theorem, maybe you can give some sort of quantitative version of that. I don't know, like, have you looked at this?
In which paper?
This is paper extremality of Gaussian states, which they use this Cauchy-Hudson version of the theorem to show that certain measures take the largest value on Gaussian states or the smallest value, like, I don't know, the conditional entropy or this kind of things.
Oh, I don't think I have that work in my mind. So
okay. Chat later.
Any questions? Let's thank the speaker again.